Okay, let's unpack this. Usually, when we sit down to write a computer program, there's this deep-seated expectation of linearity, right? You open a file, you type line 1, then you type line 2.
And you just hit save. Yeah.
Right. You hit save. You are essentially creating a chronological script. I mean, it feels exactly like handing the computer a recipe to read from top to bottom.
Well, yeah, and the human brain is heavily biased toward that, narrative structure. I mean, we read books from left to right, top to bottom.
Yeah, books out.
We experience time linearly, so naturally, when we write code, we just assume the machine is ingesting our logic in that exact same chronological sequence, like, do this, then do that.
But then you peek behind the curtain of how a compiler actually works, and that entire chronological script just vanishes.
It really does. It's an illusion.
It is. You realize the code you just wrote isn't processed as a list of sequential commands at all. Instead, it gets translated into this massive, invisible, multidimensional tree.
A tree that is silently dictating every single action your program takes.
Exactly. And to understand how that illusion works, welcome to today's deep dive. We are pulling apart the Class 16 notes from CS330 alongside Chapter 6 of the textbook, Introduction to Compilers and Language Design, just to really look at the soil this tree grows from.
And that soil is the compiler pipeline itself. Because before you can even begin to visualize a tree, you have to understand the mechanical steps a compiler takes to, well, strip away your human-readable text.
Right, because it's not a magical process. It's very rigid.
Highly engineered sequence.
Yeah.
It starts with the character stream. When you feed a file to a compiler, it doesn't see a program. It sees a massive, undifferentiated ocean of single characters.
Just spaces, letters, semicolons, line breaks.
Yeah, just raw, meaningless data.
Completely meaningless.
Right. So the first thing the compiler does is hand that ocean of characters over to the scanner, or, the lexical analyzer.
Okay, the lexical analyzer.
And the scanner's entire job is to just march through those characters and group them into recognizable logical chunks, which we call tokens.
Tokens, right.
It stops seeing the individual letters INT, and it bundles them into a single token representing the keyword int. It bundles operators, identifiers, literals.
So it's like the scanner acts like the part of my brain that stops processing individual letters on a page and just recognizes entire words.
That's a great way to put it, yeah.
It gives you a pile of recognizable vocabulary, but a pile of words dumped on the floor isn't a sentence. There is no actual structure yet.
Exactly. And that brings us to the parser, the syntax analyzer. The parser takes that sequential stream of tokens and checks them against the strict grammar rules of the programming language.
It's asking, are these tokens arranged in a mathematically valid order?
Yes. And as it validates that syntax, it doesn't just pass the text along. This is the crucial part. It physically constructs the abstract syntax tree in computer memory.
I used to think of this parsing stage like mapping out the plot of a book, like figuring out how the characters and events relate to each other.
Sure, a lot of people do.
But looking at the class notes, that analogy is completely wrong, because an AST doesn't know anything about the plot or the actual meaning of the program yet.
No, not at all. A much better way to think about it is sentence diagramming from, middle school English.
Oh, sentence diagramming. Yeah, that makes sense.
It really is the perfect mental model for this. When you diagram a sentence, you don't care if it's a profound line of poetry or, a boring instruction manual.
You're just ruthlessly dissecting it into structural branches.
Exactly. Subject, verb, predicate, adjectives, modifying nouns. The AST does exactly that to code. It takes a flat sequence of tokens and builds this hierarchical web of relationships.
And that hierarchy becomes the critical interface for the rest of the compiler's lifespan.
Right.
It sits right in the dead center of the pipeline.
Dead center.
On one side, it took in raw tokens and grammar. On the other side, it feeds that structured tree into the semantic routines.
Which handle things like type checking, which you start doing in Chapter 7.
Right. And then from there, the pipeline moves to intermediate representation, then the optimizers chew on it.
And finally, code generation spits out the actual assembly language.
Wow. So the AST really is the absolute fulcrum of the compiler.
What's fascinating here is that everything before it is just preparing the data to build the tree, and everything after it is just reading the tree to generate the final machine code.
Which brings me to something in the Class 16 notes that is genuinely fascinating. The professor takes a hard pivot away from computer science and brings in cognitive psychology.
Oh, right. The learning models.
Yeah. They start talking about memory and learning, specifically short-term memory, long-term memory, and this concept of encoding.
Right.
The notes outline this progression of human learning, moving from concepts to schema, to personal theories, and finally to worldviews.
It's a heavy concept for a computer science class.
It really is.
Yeah.
And the professor explicitly demands that you, as a student, must be willing to re-encode and fundamentally change your worldview regarding the nature of computer programs. Why is this transition framed as a psychological hurdle?
Because it requires you to actively break the mental models you've spent years building. I mean, think about it. When you first learn to program, you develop a schema based on time and sequence. Line 10 executes, then line 11 executes.
Right. If you want to trace a bug, you follow the execution path down the page.
Exactly. That schema is deeply ingrained in your long-term memory.
You literally think of your program as a timeline.
A timeline, yes, but an abstract syntax tree destroys time.
Oh, wow.
To build a compiler, you have to completely abandon that timeline schema. You must stop seeing a program as top-to-bottom text and start seeing it as a unified, static hierarchy.
So you were essentially freezing the universe you just built and looking at it from a top-down, omniscient perspective.
That's beautifully said, yes. The entire logic of the program exists simultaneously in this massive data structure.
So redefining those relationships in your own mind, forcing your brain to accommodate this top-down spatial reasoning instead of left-to-right sequential reasoning.
That is the literal definition of re-encoding your worldview.
It is a profound shift. You are no longer writing a script, you are architecting a physical structure in memory. So if we adopt this new worldview, we need to examine what the actual building blocks of this structure are made of.
We do.
The project compiler uses 5 specific C structures to define the AST, right? Declarations, statements, expressions, types, and parameters.
Yes, those 5. And we should look closely at how those are physically constructed in memory, because they aren't just abstract concepts. They are literal blocks of allocated space tethered together by pointers.
Okay, let's start with declarations. The core definition is that a declaration states the name, type, and value of a symbol so it can be used later.
Right, so we are talking about introducing variables, constants, and functions to the compiler's environment.
But how does that actually look when the tree is being built?
Well, think of a declaration node as a specialized Lego block.
A Lego block. I like that.
Yeah, in C, it's a struct called decla. So when the parser sees something like B colon boolean semicolon S colon string equals hello,
it allocates a new Lego block in memory for B.
Exactly. And this block has very specific pegs on it, fields for metadata. It has a name, peg, pointing to the string B. It has a type peg pointing to another node representing Boolean.
Okay, I'm picturing it.
And crucially, it has a next peg. That next peg acts like a rope, tethering the first declaration block to the newly created declaration block for S.
So you end up with this linked chain of highly organized metadata blocks all tethered together, keeping track of every actor on your stage.
That's right. And once you have your actors, you need them to do something, which forces the AST to create an entirely different type of structural node to handle state changes. Which brings us to statements.
Statements, the verbs of the AST. They indicate actions to be carried out that mutate the state of the machine.
Yes.
These are your loops, your conditionals, your function returns.
They dictate the flow of execution. A statement node doesn't usually resolve to a value itself, Its entire purpose is to manipulate the environment or decide which branch of the tree to traverse next.
And the third major building block handles the actual calculations. Expressions.
Right.
The text defines an expression as a combination of values and operations, evaluated by specific rules to yield a value. Calculating an integer, evaluating a string, computing a Boolean result.
Oh, wait. Also, here's where it gets really interesting, because the textbook draws a hard line here, and I have to push back on this boundary.
Okay, push back. Let's hear it.
It says an expression's job is to yield a value, and a statement's job is to change the state. But what about something like x++? It evaluates a value, but it also increments the variable, mutating the state. It's doing both. Is the AST just having an identity crisis when it encounters that? Like, how does it categorize something that acts like both?
Well, it seems like a glaring contradiction, right? But it actually exposes exactly how rigid and mechanical the compiler's categorization process is. How so?
Because from the AST's perspective, there is no identity crisis at all. The compiler doesn't categorize nodes based on their downstream side effects. It relies entirely on the strict grammar of the language.
Oh, so it only cares about where the token sits syntactically.
Precisely. If the grammar rules of the language dictate that x++ is allowed to sit in the syntactic position of an expression, say, inside the condition of a while loop,
Right.
then the parser will construct it as an expression node. The fact that evaluating that node happens to have a side effect that mutates memory, well, that's a semantic
The
problem.
parser doesn't care.
Not at all. It just says grammatically this is an expression, so I'm grabbing an expression Lego block and snapping it into the tree.
Okay, that makes a lot of sense.
Yeah.
The parser is just following structural blueprints. It's not trying to predict the future of the program state.
Exactly.
And this brings up a massive engineering question that the class notes highlight. How many node types do we need?
Oh, that's a golden question.
Right. When you are physically writing the C code to build this compiler, you have to decide how granular your Lego blocks need to be.
If we connect this to the bigger picture, you really have to strike a balance. If you make too many specific node types, your compiler's code base becomes just bloated and unmanageable.
Yeah.
But if you make too few, you can't capture the necessary nuances of the language.
The notes use for, if, and else as a prime example of this tension. Since those three structures all contain blocks of executable statements beneath them, the naive approach would be to just make one generic block container node and use it for all three.
But you mathematically cannot do that because the structural mechanics required to execute them are completely different.
Back to the pegs on our Lego blocks.
Yes. Think about a for loop. It requires a highly complex node. It needs an initialization peg, a condition peg that evaluates to a Boolean, an increment peg to update the loop counter, and finally, a body peg pointing to the statements inside the loop.
4 distinct pointers.
Exactly. Now look at an if statement. An if node needs a condition peg, a body peg for when the condition is true, and crucially, an optional else peg pointing to a completely different block of code if the condition is false.
And a for loop never has an else fallback.
Never. And an else statement itself, it doesn't have a condition peg at all. It just acts as a default execution body.
Okay, yeah. So if you tried to force all three of those into a single generic C struct, you would have a node with a dozen fields, most of which would be empty NLL pointers, depending on the context.
It would be a massive waste of memory and incredibly confusing to traverse. So you are forced to create distinct, highly specialized structures for each grammatical concept.
You are meticulously tailoring the physical data structures to match the grammatical reality of the programming language.
Exactly.
So what does this all mean when we put it together? We have this massive web of tethered Lego blocks representing our statements, our expressions, our declarations, but we need to address the actual name of this structure, the abstract syntax tree.
Right, the abstract part.
What exactly is making this abstract? What is being left behind in this translation?
The word abstract is really doing the heaviest lifting in the entire acronym. When we call the tree abstract, it means the structure intentionally and frankly, ruthlessly discards the superficial details of the parsing stage.
Walk me through an example of what gets burned away.
Think about mathematical notation. The human formatting of code is highly variable. Some programming languages use infix notation, where you write 3 plus 4.
Sure.
Some use prefix notation, where the operator comes first, like +3, 4. Others use postfix, 3, 4 plus.
Right.
During the parsing stage, the compiler cares deeply about that specific order. If you feed prefix notation into a compiler expecting infix, the parser will throw a massive syntax error because the sequence of tokens violates its grammar rules.
So the parser demands you speak with the correct regional accent.
That's a great way to frame it. But once the parser validates those tokens and physically constructs the AST, the tree simply does not care about the original text formatting anymore.
It's gone.
The syntax rules of how the human typed it are burned away.
It just distills it down to the pure mathematical relationships.
It creates a single ADD node. The left child rope points to the value 3. The right child rope points to the value 4. The syntax is gone. Only the pure structural semantics remain.
That is wild.
The tree is completely abstracted away from the textual representation.
Which is incredibly powerful, but actually building this abstraction manually in C sounds like an absolute nightmare.
Oh, it is.
The textbook demonstrates how you would construct these nodes by hand without a parser automating it. It's not something you'd ever want to read aloud.
No, please don't.
You are essentially writing deeply nested C functions, passing pointers into other functions, creating Russian nesting dolls of memory allocation, just to represent a simple mathematical operation.
Writing it manually is incredibly tedious, and the textbook knows that.
Yeah.
It forces you to look at that manual construction so you deeply understand the mechanics of memory allocation before it teaches you how to automate the process with parser generators.
Right.
But because looking at nested C code is an awful way to verify if your tree is built correctly, the textbook provides a massive lifeline: visualization.
Yes. The GraphViz DOT format,
Instead of writing endless print statements trying to debug your pointers in a terminal,
which we've all done.
which is miserable, you can write a recursive function that walks through your AST and emits text in the DOT format. You feed that DOT file into a renderer, and it physically draws the tree for you.
You literally get an image file showing circles for every node and arrows for every pointer.
It turns the abstract memory structures of your compiler into a visible, tangible map. You can instantly see if your if statement accidentally tethered its else block to the wrong parent node.
Oh, that saves hours of debugging frustration.
So many hours.
And this perfectly sets up why the Class 16 notes explicitly label Chapter 6 as your BFF,
Yes.
your best friend forever. The professor is emphasizing that this chapter contains the exact granular details required to implement the parser correctly. The nuances of how these nodes connect are so easily missed until you are staring at a broken tree.
The reason Chapter 6 has to be your best friend is because building this perfect abstraction is the only way you survive the next phase of the compiler pipeline.
Right.
By stripping away all that messy, human-readable syntax and creating a rigid mathematical map, the compiler is fully prepared for Chapter 7's semantic analysis.
And semantic analysis is where the compiler actually checks if the code makes logical sense.
Yeah.
Right. Not just grammatically correct, but logically valid.
Yes. Imagine trying to verify that a variable is the correct type by scanning back and forth through a massive, flat text file.
Oh, that sounds awful.
You'd have to constantly search for where the variable was declared, check its scope, find the operator, and cross-reference everything. It would be incredibly slow and complex.
But with the AST, you don't have to search text at all.
You just walk the tree. Because the AST has organized everything into these neat Lego blocks, the compiler can perform a simple recursive traversal.
Okay, walk me through that.
Well, say it lands on an ADD node. It slides down the left rope and sees an integer block. It slides down the right rope and sees a string block. It immediately realizes that the types do not match. You cannot add a string to an integer. And it throws a semantic error.
The abstraction makes that analysis exponentially more efficient.
Exponentially.
It really is a beautiful piece of engineering when you step back and look at the whole journey. You start with a meaningless ocean of text characters. You group them into tokens. You validate them against a grammar. And then you construct this pure, timeless map of logic.
But as we discussed at the beginning, understanding that beauty relies entirely on your willingness to re-encode your worldview.
Right.
You cannot build these structures if you are still clinging to the idea that code is just a linear script.
Which brings us to the stakes of this week. Because this conceptual leap from linear scripts to hierarchical trees is so huge, you cannot just passively skim the readings and expect it to click.
No, definitely not.
This level of abstraction requires you to get your hands dirty, which is exactly why your deliverables this week are structured the way they are.
Yeah, the syllabus has some crucial deadlines approaching that are specifically designed to force this paradigm shift.
Friday, March 6th, is the first major hurdle. You need to have finished reading the compiler's book, Chapter 6, your BFF on the AST.
Read it closely.
But reading isn't enough. Also due on that Friday is Lab 5. Now, Lab 5 is technically optional for extra credit. But given the sheer density of the memory allocation and pointer mechanics we just talked about, applying this practically in the lab is the only real way to ensure you survive Chapter 7.
Yeah, if you don't build the Lego blocks yourself in Lab 5, the theory isn't going to stick.
Then, on Sunday, March 8th, you have to submit your journal entry for week 7. And the syllabus strictly mandates the 2-1 rule for this.
And that rule requires a minimum of 2 paragraphs of reflection on the material and 1 original quiz question that you generate based on the concepts.
2 paragraphs, 1 question. Do not leave that reflection until Sunday night, because synthesizing this worldview shift takes actual cognitive effort.
It really does. You need time to wrap your head around it.
So we have tracked the incredible metamorphosis of your code today. We've watched it evolve from a flat list of commands into a massive, invisible tree of pure abstracted logic. But I want to leave you with a final thought to mull over as you dive into the readings.
Oh, I like where this is going.
We established that the abstract syntax tree intentionally strips away all the specific human-type syntax of a programming language. It burns away the formatting, the semicolons, the regional dialects of the code, leaving behind only the pure structural relationships.
Right, the universal map.
If that is true, if an AST is truly a universal mathematical representation of a program's core logic, could an AST be used as a master key?
A master key.
Could you take a program written in a language like C, parse it into its abstract syntax tree, and then seamlessly traverse that exact same tree to generate code in an entirely different language, like Python or Java?
This raises an important question. I mean, if the syntax is completely gone and only the universal logic remains, what is actually stopping that tree from growing leaves of a completely different language?
Exactly. That is the true power of abstraction. Think about that as you build your nodes in Lab 5. Until next time, keep diving deep.